Good morning. I'm going to go through a brief summary of the feedback we received from the various proponent experts and resources post-workshop 2. So it'll be very brief. We'll cover information from this long list of individuals in alphabetical order. This is the basis for the order. So basically, I'll stop briefly after each one if there's any questions on each one, so to get through it. So first, we had information received from Abramson et al. For the ASK 2014 model, having to do with the effects of removing Class 2 events on the aleatory variability terms. As you remember, Class 2 is our new definition of what used to be called aftershocks. Basically dependent events that occur in close proximity to the rupture of the main or Class 1 events. And in the ground motion development, in development, most of the modelers either treated these as a separate class of events and accounted for differences in them, or did not include them at all in their ground motion model development as a part of NGA West 2. And the question is then, the Abramson and the ASK model included these events in the calculation of their aleatory variability, and so what would be the effect if they were events were not included? Basically, there were small changes to the values of phi, slightly larger changes to the value of tau, which is the event-to-event variability, and these effects vary with magnitude and with period, and slides were provided that indicate, for instance, this example is the effect on phi at 2 magnitude ranges, down to magnitude 4, which is the blue squares at the top, and the green triangles you can barely see. So you can see at this magnitude there's hardly any effect of the Class 2 events. And then the red circles is phi at magnitude 6 and larger, and it's slightly larger without the after Class 2 events at high frequency and slightly lower low frequency, but basically a relatively small effect on phi. The effect on tau is a little larger, basically resulting in slightly smaller values of tau across the full magnitude range, and at small magnitudes, and slightly larger values of tau for the larger magnitudes at high frequency, and basically similar results at low frequency. So that's the information we received from ASK. Any questions? We received a lot of additional information from Eckhart et al. On the ASB 2014 model. Particularly, the information we asked for were questions on the effect of earthquake depth, and they examined the effect on their median motions, basically in terms of the event terms, and they found that no significant trends with depth for the normal earthquake ground motions. Strike slip earthquakes showed some decrease at long periods. Reverse earthquakes showed basically a decrease with increasing depth at all periods. And these effects were somewhat stronger for moderate magnitude 5 and 6 earthquakes than for smaller magnitudes. It should be pointed out that the ASB model uses joiner bore distance as a distance measure rather than rupture distance. So the depth effects here would be somewhat different than you would see in the depth effects in a rupture model, because it basically has, at the same joiner bore distance, deeper events are further away. There's the plots that he sent showing the effects, just basically the event terms as a function of the depth for the different styles of faulting, showing in the center the reverse earthquake, showing a trend at basically the frequencies. We start at VGA 5 hertz, 0.2 seconds, 1 second at the bottom, and then 2, 3, and 4 seconds. And you can see the center panel is reversed, and there's basically a depth trend in all frequencies for that style of faulting in their data set. Also mention that reverse data set is probably the lowest populated data set in terms of the style of faulting in their data. Additional questions we asked about the effect information on the aleatory variability. Typically, they show had larger variability, aleatory variability than the NGA West 2 results. They provided estimates of tau and phi for their data set, and they concluded that the differences in the estimates of phi, the within event variability, dominated the difference between NGA and the European aleatory variability models. They also did an evaluation of tau and phi using only data from well-recorded events, and their results indicated they only saw a reduction in tau at short periods when they used well-recorded events instead of all events. And they presented some magnitude effects on tau with vary with period. Their data set that typically does not include a lot of events above magnitude 7, so or fewer events to say. We don't all have a lot of events above magnitude 7, but they have fewer perhaps than are in the NGA set. And so they're basically comparing results between 5 and 6 and 4 and 5. And their magnitude effects varied somewhat with period, shows a slide there. And they also had a very large bump in phi at long periods, and they concluded that was due to estimates from large distance events, from large distances beyond 70 kilometers. So this is basically a plot showing that the magnitude variation in tau, the red is above 5.5, the black is below 5.5. You can see the lines crossing. Basically getting somewhat larger at short periods, and lower taus at longer periods for events above 5.5. And on the lower right, the plot of effective distance on the estimates of phi, with large phi from data from long periods, long distances. Any questions? Then we got a little bit of information from John Anderson. He provides. Yes.
Just like all technical support, turn it on first, right? Is it plugged in? So I would encourage, don't wait for Bob to talk for an hour and then ask him questions. So go ahead and interrupt and ask now, because there's too many different topics. Our purpose of bringing you all here was not to have you listen to us. We want to get feedback from you. So I think if there's any questions, interrupt him and go ahead, use that.
Bob, so they explained that the difference between NGA and their model in phi, that's what they said, but they didn't say why.
No, they didn't say why. They have larger phis than, but they didn't say why. They did, when they looked at well-recorded data versus basically earthquakes where they have multiple recordings per earthquake as opposed to just 1 or 2. They did not see a significant difference in anything but tau.
Okay.
And so they didn't explain.
And then I remember when Akar was here, I think in the last workshop, he was not sure about applicability of their model to California, and he wanted to check it or somehow. Have you received any feedback from them?
Not on that topic.
Okay.
Okay, anything else? Racing on to John Anderson. John provided papers on very large ground motions, which is a topic of interest for many people. These are the basic papers he had developed initially in BSSA, a summary or database of large ground motions. He presented lists of some papers on some other aspects of ground motions, such as the trampoline effect and slap-down phases, and then also indicated that he had recently completed an updated database of large ground motions, which is available in a USGS open file report. He had some questions on various aspects of proposals for the causes of extreme ground motions, which were discussed briefly between him and other investigators, but he concluded that there are significant evidence for motions that are significantly larger than maybe what has been recorded, so that we need to deal with the issue of very large ground motions. And then indicated that his compilation, the updated compilation, could be used to test distributional shapes at very large ground motions, which is something we are exploring. So any questions about feedback from John?
Bob, his evidence is then looking at geology, or is that what, when you say he has evidence of ground motions larger than have been recorded?
Well, just basically anecdotal information about, things moving, things flying, leaving the ground. Basically evidence that, not from geology, but from just observations, reported observations of potentially very strong events. So basically that things that, basically I think his conclusion is that we cannot assume that we've got the largest ground motion in our database. This was presented at a working meeting in January. Last time, workshop 2, we did not. Gail Atkinson couldn't be here, so we have 3 broadband simulation methods that that have been implemented on the SCEC and have passed the validation. And XSIM is one of those. And so Gail came and presented a summary of her model and answered some questions. She had a long presentation, and this is the summary of the basic principles behind the code XSIM, which is basically a stochastic finite fault modeling program where the fault plane is, again, discretized into a grid of equal area subsources. Each source is modeled with a stochastic point source model with basically a Gaussian white noise of the underlying spectrum, including source, path, and side effects. The sub-sources are initiated by a rupture front, and then the compute time histories, which are delayed by the initiation time and then summed in the time domain at the site. And the key inputs are the subsource stress parameter, the spherical attenuation model for the Fourier spectra, the site response model, where site responses includes amplification all the way from the source up through the crustal velocity gradient. And the product of that is basically synthetic accelegrams. If there are any questions on actually all that work, I'm sure there are people here who can do it better than I. Then we had a number of questions were asked each of the broadband platform modelers to discuss, and these are Gail's responses for XSIM. First one, can the model be applied to both surface and buried ruptures? And the answer was yes. It does not distinguish between buried ruptures or surface ruptures. It's a simple generic model which just uses path-specific. It does not use path-specific Green's functions to measure attenuation. Just use typically 1 over R or 1 over R to 1/2. A very simple empirical attenuation function to model path from the subsource to the site. Question, is there any limitation on how large it can be used? And she indicates no, there's no limitations at large M. Is there questions about whether there's limitation on distance? And she would basically recommend not using 0 just due to numerical problems in the code, basically using a very small distance for close distances rather than 0. And the general question was how kappa was incorporated in the simulation. And for XSIM, the kappa is incorporated through the modification of the source spectrum as they reach the site in the typical point source application approach, basically modifying the Fourier amplitudes for kappa. Questions on those responses? Other questions that were general questions for the broadband modelers was, is there any issue with using the model at very smaller magnitudes, say down to magnitudes 5.5? And their response was no, but small magnitudes are not an issue, but at that small magnitudes they would just recommend just using point source representation. Again, the question about buried and surface ruptures for hanging wall effects, and the response is XSIM does not, again, distinguish between buried and surface ruptures. basically similar answers to the answers on the previous page, and again recommending that would not use 0 as a distance, rather a very small value due to numerical issues in the code. And they also indicated that it was not really intended as a near source estimation tool. Any questions on that? Then presented some plots here in terms of looking at the behavior of the results of their simulation and questions whether they appear to be reasonable. In terms of the hanging wall effect, she basically indicates that the behavior on the hanging wall arises from simple geometry in their application, how far away each subsource is from the observational point, and they basically are summing the effects of these simple point sources at each of the planes to model the effect. So behavior was as she expected. And the same for effective depth. Basically, it's just how far away you are from each point source and how they sum together in time. And the shape of the spectrum, in terms of how the spectrum look, basically her response is that the behavior at XM at low frequency is governed by the assigned seismic moment, and the comparisons from these with the various models to her results are as she expected from previous implementations. She notes that XM does not attempt to explicitly model surface waves or basin effects. It just uses again a very simple path term. And the comparisons at high frequency are basically governed by the assumption of the appropriate stress parameters that goes with each of the sub-events.
That's good. Christine? Gail said that the model was not really a near-fault tool. In the validation effort, did you guys have anything, indication that it did not work as well at short distances as the other models?
Well, it depends what you define short distance. I can look up our results.
Let's say less than 5 kilometers.
Let's say less than 2 or something.
Yeah, it's probably less than 2, and I don't think we have much data there. I think that our shortest distance is 1.9 or it's near 2, and I think the problems really come nearer than that. And I think when Jeff is going to show his results later, you'll see what it does. Ground motion should go crazy. So I'll take a look while you guys keep on working and see what the data we have to constrain it.
And just to comment, there's probably a frequency dependence on that. It would be my speculation. So as you go to higher frequencies, it probably performs better in close. But as you go to very low frequencies, my speculation is that may be with the context that Gail's talking about.
Doug?
I did a quick review of the validation of the SCEC broadband platform, and there's a table that shows breakdown different period ranges and distance ranges. So we have a bin 0 to 5 kilometers, and XSIM is the performance at short periods is comparable to the other 2 methods that we have, and at longer periods, it's also comparable.
So there was some question, additional question came up in discussions with Gail, and she provided some feedback post the feedback. And the question first was how random slip distribution is used in XSIM. And her response is basically they generate a random set of weights for sub-events, for slip on each of the sub-events. And then those are normalized to sum to 1. And they basically represent the fraction of the total moment that's assigned to each sub-event. Then once those have been assigned for a particular realization, the sub-event source frequency, sub-source point source high frequency amplitudes are then adjusted by an overall dynamic corner frequency, which depends only on the cumulative size of the rupture area, and it's unaffected by the sub-event seismic moment. And the effect of these slip distributions is just to modify the amount of moment released in each sub-event. And she indicates that her results show little sensitivity to the slip distribution on average. So basically, she argues that she can do only a few number of realizations to basically capture that effect, and you don't need to do a lot. And that basically the hazard or the ground motion results are not very sensitive to that, although you may get some individual sites that might be near a high random cluster of events that would produce higher ground motion. So this is, I guess, somewhat different than the way slip distributions that work in the other models. And then there was a question about crustal amplification that she's used in her validations, and basically in terms of frequencies above what are shown in some of the figures, and then she indicated that they basically cap the amplification at the largest value shown on the figures in their results for higher frequencies. Any other questions for Gail? Then on into the Bs. Jack Baker presented some information on the effect of spatial correlation on estimates of aleatory variability. Basically, as Norm indicated, basically the fact that in our typical ground motion assessments, we treat sites that have some spacing, some separation on the order of a kilometer or more as being independent estimates of ground motion, and in our terms of a calculation of aleatory variability. But in fact, there is perhaps, if there is spatial correlation in ground motions, then that would affect the independence of those measurements from adjacent but not co-located sites. And they had done some preliminary evaluations of NGA West 1 data, which indicated that spatial correlation seemed to indicate that there was a slight reduction had different effects on the different types of aleatory variability, the station-to-station variability, the within-station variability. And the initial results of those were presented in a paper in BSSA, and one of Jack's former students, who's now at Virginia Tech, is actually working on this evaluation for the NGA West 2 data set. So we should have some results of the effect of correlation to use in our estimates of aleatory variability to carry forward into this model. So any questions about Baker? Okay. As we presented in workshop 2, one of the models we were looking at from the European set was the model by Bindi et al. In 2011, which showed, as shown by the orange line, basically they were having a very large magnitude scaling above magnitude 7. Especially Bindi et al. 2011, their data set is primarily limited to earthquakes smaller than 7. And then Bindi et al. 2014 presented an update to the Bindi et al. 2011, which is shown in here on red line. So they've adjusted the magnitude scaling to magnitudes above 7 dramatically at some frequencies. As you can see, the dashed orange line is dropped down to the red line. This is a comparison of magnitude versus ground motion amplitude at a distance of 10 kilometers for strike-slip earthquakes. But at some frequencies, like 5 hertz in particular in that range, their 2014 model is very similar to the 2011 model and shows much higher magnitude scaling above magnitude 7 than most other models. As we move to longer frequencies, their magnitude scaling is now consistent with magnitude scaling from many of the other models. So there still seems to be some difference in the intermediate frequencies from the Bindi et al. Update, and perhaps is limited to the fact they don't have much data above magnitude 7. Any questions on?
Do we know how much they had? Number of recordings or earthquakes?
Don't know, but we can certainly find. Then we had information from Day1 and the BSSA model on several topics. One of which was the question about the so-called bump in tau, which we observed in the residuals, the bump in the event-to-event variability around 10 hertz. And Day1 performed some simulations using from magnitude 4 and magnitude 4 and magnitude 6.5, using a range of stress parameters and looking at the effect of differences in those on ground motions. And the plots on the right basically show his results for on the top magnitude 6.5 and on the bottom for magnitude 4. And they concluded that the bump in tau could, for large events, is probably not a source effect, but could very well be some interaction of site effects with our average site effects recorded with the motions in a particular set of motions. But for smaller events, such as magnitude 4, there could be a stress source effect that may produce the bump in tau source effect interacting with kappa, and that further study is needed. There was a question from
Robin. He said, explain the axes, the vertical axes.
Vertical axes are magnitude, spectral amplitude versus spectral amplitude for a stress drop of 100 bars. Sorry.
Just normalized to
Just normalized to a stress to a ground motion predicted for a 100 bar stress drop.
Bob.
In an earlier plot, you showed the bump seemed to be at a much higher frequency for the smaller earthquakes than the larger earthquakes. Is that explained by? It doesn't seem to be explained here.
No, I don't know that it's much higher.
Yeah.
On the
Well, there
plot,
was a dramatic difference on the plot, if you want to.
Well, we see, for instance, in looking at least when I've looked at the residuals, I see a much stronger bump in tau at large magnitudes than I see at small magnitudes. In our looking at our Cho and Young's data set.
So I'm just referring to the plot you showed earlier.
Yes.
If you wanted to,
Well,
sorry.
basically,
Sorry to make you. If you want to go back to that, I don't know.
Yeah, we can. Well, there's another plot coming up. We'll show it somewhat to show
Okay,
that, but
right,
basically
fine.
here,
But
there is no. He sees nothing at magnitude 6.5. It says it's not a source effect at all. It's basically flat across the frequency range. But he does see, which is what I had argued in some back in workshop 2. But at smaller magnitudes, if you simulate down to magnitude 4, you would perhaps see a source effect. So that there was some interaction between the differences in stress drop and differences in kappa that might show up as magnitude 4.
Okay. Well.
So the basic conclusion was that it's a mixture. But at larger magnitudes, he does not think it's coming from the source. And at smaller magnitudes, it could be coming partially from the source. Yes?
I think maybe you mentioned also, I think we have to dig into this issue a little bit more. We have to dig into this issue a little bit more just to understand more.
Then other thing we asked for BSSA, they provided standard errors of their estimate of the normal faulting effect, the normal faulting factors, and this is a plot of their estimates of the standard error in the normal faulting term. As the NGA data set was not really particularly strong in normal faulting data, the uncertainty of those parameters are important for our application to the host source zone in Arizona, which is the normal faulting arena. So they provided information on their estimates of the uncertainty in the normal faulting factors, and noted that the very large increase in that standard error at long periods was basically due to a rapid decrease in the amount of data. They provided, without any real analysis, some hanging wall residuals as a function of dip and RJB. The issue where it's very difficult to see the effect is right here at 0, which is on top of the hanging wall, which is where we have most of our uncertainty as to what the hanging wall term is, and there's not a lot of data to evaluate it empirically. And finally, a evaluation of the intra-event or phi as a function of distance and of region, indicating that, as others have found, that their Japanese data have significant higher phi than other data sets. So that's, I think, what we got from BSSA. Any more questions? Tom Heaton provided some information or issues to consider in developing the ground motion models. First, basically, the effects of very large, long-period ground motions are likely nonlinear, and we should evaluate using we should definitely consider use of appropriate time histories for those evaluations for analysis of the effects at long periods, if these effects are important for the structures we're evaluating. Basically, to not use a modal analysis at very long periods. The second point was that the spatial distribution of slip is a key parameter for the nature of near surface long period motions, and we should really look at the characterization of the statistics of the slip on segments of a fault near the source, near the site, in terms of evaluating the distribution of very large long period ground motions. And again, the third point, emphasizing again the importance of examining the form of the upper tail of the ground motion distribution and the departures from the assumption of log normal, which is our typical default ground motion. So these were basic issues that we should be looking at as a part of our ground motion development. Any questions on that?
Really, at least for structures of nuclear plants, maybe not for slushing and so on, the periods are not that long for this specific application. Maybe for tall buildings, base isolated structures and so on, that is correct. So I'm not sure for most of the structures that you're concerned that first bullet is really serious issue.
Yusuf, you're right. Our focus is on higher frequencies driven by things that cause equipment failure as opposed to structural failure. But we're going to go through some of these in more detail today, so you'll see some more response to this. The bottom part, clearly, we need to deal with. That affects us is the distribution of the upper tail. Tom, you wanted to add something?
Well, my comments were in light of the original question from the NRC about reviewing procedures in light of what happened in Fukushima. And so the question is simply if there are some issues like sloshing modes, especially, I don't know, there may be others, but the obvious one is the question of sloshing. If those are issues, then we should be very circumspect about describing everything with linear response spectra. And furthermore, the long periods are almost certainly power law and not log normal kinds of distributions. So it may not be an issue, but if it is, we need to consider it.
Okay. Then we had some feedback from Ed Idris on the Idris 2014 update to Idris 2008. Provided some discussion on modifications to his model. The basic changes from the 2008 model were inclusion of VS30 scaling for sites with basically it's a model for sites with VS30 above 450 meters per second, and based on the updated data set, he now included a VS30 scaling term, where before he had just a constant amplitude as independent of VS30 between 450 and 900, and then a change at 900 and above. But now he has a linear term with log VS30, and he's included a quadratic magnitude scaling term in this assessment. We asked about evaluation of normal faulting factor, and he felt that there was insufficient data for him to, in his data set, his subset of the NGA data set, to quantify this, although he thought the values on the order of minus 0.05 to 10% appeared to be a reasonable number, but he did not evaluate it. There is some issue about prediction of his extrapolation of his ground motion model into distances of 1 kilometer and less, where there appears to be significant changes in the behavior of it, and he needed to examine that further, but we haven't received anything in addition on that. And I believe right now we are not using it at 1 kilometer. He did not find a significant trend of depth in the data he looked at, and he did not constrain a hanging wall factor in his model because he felt that there was insufficient empirical data in the NGA West 2 database to constrain a model just based on empirical data, which is why most of the other developers went to use of the simulation data to help constrain that. So any questions on Ralph?
Bob, you keep mentioning depth, and I presume you mean hypocentral depth, just to be clear.
It could be hypocenter or top of rupture, depth top of rupture. Some representation of depth in the model. The NGA West 2 models have, 3 of them have depth terms in them. 2 of them use depth to top of rupture, and 1 uses hypocentral depth.
Okay.
Those.
So this depth issue, so it seems contradictory to the other models that you just mentioned. So how come we saw this very strong depth in models as well as other GMP developers? So somehow,
I think part of it, Yusuf, is he's looking at raw total residuals, and if you do that, then your recordings per event and so forth can make it harder to see through it.
Yeah, so Idris does not separate, in his analysis, he does not do a mixed effects model where he gets event-to-event variability and intra-event variability. And where at least we see it in terms of evaluation is looking at the event terms and then those trends with depth. So he does not do his regression that way, so that may have something to do with it. We don't know for sure, but again.
So Bob, the USGS in their national hazard map reviewed all the documentation for the NGA West 2 models and chose to give the Idris model lower weight because of a lack of sufficient documentation. Do you consider your interaction with Idris to be sufficient to give it equal weight, or how did you treat the model?
We
in
haven't,
the use of it. I know it'll come up later, but just
so we haven't actually given models weights yet. So we are including it in our set of models to look at in terms of where they play out in the visual or the distribution of ground motion predictions, but we're not to the point where we've actually given it a weight.
Other than at short distances,
Yes, where we've
only used it for 3 kilometers and greater at this time because of this issue on its extrapolation. Our plan, you'll see later on, our plan is not to use it on the hanging wall side because it doesn't address those factors at all.
Or to use it for estimating normal faulting effects because it doesn't address those either.
What about large distances? Because
large distances, we are evaluating how well the models do against data from Arizona at large distances for data recorded in Arizona from California earthquakes at large distances. So models that do well against that data will be considered in terms of the shape of the attenuation curve.
Because for the national hazard maps, one reason of lower weight was not applicability for larger distances.
Yes, well, yes. But that data, we're using the data that's been, which were discussed in January, but I think we'll be presented again later. Basically, we have data recorded in Arizona from Maricopa, and then a set of magnitude 4 to 5 earthquakes that are occurred in California. We can use that to evaluate whether the various models are matching the appropriate attenuation shape. And that will be the basis for their inclusion or exclusion in our assessment. So anything else on IDRIS? And then we had some additional feedback from Kevin Maeda. First, he provided a couple papers on the Wells, Nevada earthquake, where they investigated, where they indicated there was some significant source directivity and higher static stress drop than other events in the region. And we're in the process of looking at data from Wells, Nevada, in terms of comparison with recordings from other other earthquakes. Particularly, I think we're looking at estimates of peak velocity from that data set. And he also provided results of their large inversion for Q in terms of data for individual frequency bands from the US array that we could use to estimate Q and ADA along particular paths if we needed to use that. Anything else briefly from Kevin? Palo Verde, there was an issue of whether there were any fragile geologic features that could be used to constrain ground motions. And there was a presentation given at the Palo Verde source characterization workshop describing what kinds of data were available in Arizona, but basically nothing indicating that there was nothing that had been used to constrain ground motions in Arizona, and there was no real evidence of any of these features near, there was no clear evidence that there were any of these features near Palo Verde, and at this time that there doesn't seem to be anything more being done at this point on that subject for Palo Verde. Cho and Young's, we were asked to provide tables of the uncertainty and the estimates of tau and phi, because we basically we did estimates of the uncertainty in those estimates, and we have those for the project. And then the other one, we presented some additional evaluation of our residuals in terms of looking at, again, at the issue about the bump in tau at short periods. And for the smaller magnitude data sets, magnitudes less than 5, there are a lot of recordings, multiple sites with multiple earthquake recordings. And so we examined that using a mixed effect model with cross classifications, basically including a model for a random earthquake term, and then a model for a random site term, and then a set of residuals. So basically breaking phi into phi site to site and phi individual site estimates. And there's sufficient data to do that analysis for this data set, which is somewhat similar to what Linda is doing, looking at single station phi. And when we do that analysis, this is shown on this plot. The top plot is a plot versus period on the horizontal axis of tau, which is the event-to-event variability for magnitudes between 3 and 5.5. The red curve is the analysis of tau from these events when the site term, the phi term, is all lumped together, the augmentatory variability. And the blue curve is when you separate the phi term into site-to-site variability and within-site variability, phi SS and phi S2S. And you can see that analysis basically results in a significant reduction in the bump in tau at around 10 hertz. And I think this is what you were mentioning, Ken. It's a little bit higher here than for these magnitudes. It's a little bit higher than it is for the larger magnitudes, where it's down around 0.1 second or 10 hertz. Is that what you were? And the bottom plot, the red points are total phi when, and then the blue and green curves show when phi is separated into its two components. The phi S2S are the blue points, and the phi SS, or single station phi, would be the green points. And you can see that basically we get a bump or higher variability in the phi S2S, or site-to-site variability around in that same frequency range, and that the phi SS is flat. So basically, in this analysis, we've transferred the variability. We transferred the variability. This bump in here has now been transferred, showing up as actually a site-to-site variability, indicating that, again, reinforcing the concept that we had proposed, Cho and Youngs had proposed anyway, that the bump we're seeing in there is actually a representation of variability in the average site recording individual earthquakes, and is not a source term, but it still is a site term that needs to be captured in the site part of the evaluation. So that's a feedback we got from CY14. And getting all the way to Z, John Zhao gave us some additional information. There was Zhao et al. In 2006 developed a GMPE for predicting for evaluating ground motions from both subduction and crustal earthquakes, driven largely by Japanese data, but augmented by some larger crustal events from other regions, which had relatively strong magnitude scaling. And then Zhao and Liu in 2011 published a paper indicating that looking in detail at the crustal events, that the magnitude scaling above magnitudes about 7 appeared to be very weak in their evaluation. And so we had asked them about how to implement that model, because they just discussed it but didn't really provide us an updated model. And the additional feedback we got was that basically consider that what they found from looking at the data was at short periods very weak scaling above magnitude 7.1, and at long periods essentially negative scaling, and which they recommend never to let go negative, but to set to 0. So the implementation we got from him was, the concept of implementation was basically consider simply 0 magnitude scaling for magnitudes above 7.1. And that also indicated that he found similar effects for large subduction events, but the reduction in magnitude scaling was not as strong as the reduction he saw for crustal events. Ken?
Certainly the NGA West models and maybe others show that sort of flatness in the magnitude scaling is limited to short distances, and it tends to then start scaling more at large distances. Did they give you a distance?
No, they weren't. The way this was presented was it was done as in terms of event terms. So they basically fit individual events with basically random effects for slope and basically the distance terms, and then obtained event terms out of that and plotted that the event terms were flat in terms of magnitude. We are evaluating, going through the process of evaluating it in terms of actual, just as a function of distance. And some preliminary evaluations I've done indicate that it's very flat. It is very flat and close. But ultimately, we would expect that at some distance we should see magnitude. Otherwise, we wouldn't be measuring magnitudes. But
okay, thank you.
So I think we need to look at that in terms of that's the focus of our evaluation is what does the NGA data set say about this at larger distances? Because the primary place where we have significant amount of is a large magnitude information input to the hazard is for Arizona and the large events in California, which are at distances of 200 kilometers. So that's where we need to evaluate whether his model should be, how it should feed into our evaluations. And this basically implementation of that model would just say that basically you would come up to magnitude 7.1 and just go flat across this, which is not unreasonable for compare the range of estimates from other models at short periods. But as you get to longer periods, it would seem to be a dramatic departure from other implementations of ground motion models.
Bob, as you just mentioned, we have seen it for long time at short period, and there is a physics behind it. But long period, I don't know. What is the period of the right-hand side? 3 seconds.
3 seconds.
So at 3 seconds, or even I remember from last time, maybe 5 seconds you get saturation, and now it says oversaturation. This is definitely, it's not what we see.
Yes. But as I said, he's evaluating event terms, so it's hard to see how they play out in the entire data set. So we are looking at what we can see from the data at large distances. And that's that. Doing my best to give us time. Christine.
So I looked at our validation to go back to XSIM and the issue near field. So we only have 5 data points between 0 and 5 kilometers across all 7 events. Okay, so it's really hard to draw conclusions. The one that's the closest is Satori, within a kilometer, just 0.9 something. And then for this one, XSIM performs really poorly, but it's 1 data point compared to the other simulations. Then we have Lenders at 2.2, Loma Prieta, 2 records within about 4 kilometers, and North Palm Springs at 4. And for these, the results are comparable. But again, statistically, it's a total of 5 points over all the stations. So I just wanted to clarify that. I don't think we have enough to really say where the method starts to not work well, other than Gale's assessment.
Other than 0, where something goes bad, right? At 0 distance, we know there's a numerical problem.
Yes, but it's the case for most models, right? It's directly 0.
No.
You don't have a singularity? Okay, only XSIM then. But yeah, but we don't have any proof.
Yeah. So.
Any other questions for Bob? He got through this too fast. Almost surprised. So some of you have seen this the second time now, because Bob went through this in January, so that's probably part of it. Is there anything that you didn't think you covered enough?
Oh, that I didn't cover. There was a lot. I don't think so.
I mean, one of the issues that Yusef brought up was the fee from Akkar's model. Right? Why it's a lot higher, and we don't know why.
He didn't really say why. He did look at large, well-recorded events versus poorly recorded events, but he didn't. I don't know if they investigated whether, any way to investigate whether they had better metadata for these versus other data. I mean, that would be a possible difference with
the site or the distance.
The site of the
term.
distance terms is not as well defined as we do at NGA. It was and also how wonderful NGA is.
And also, I remember he said, I don't know if it's really the case, he said processing of the records in Europe. He was not sure about the quality of that. I don't know if really that's the source of it. The other issue with Akkar, I remember, as you mentioned, since they don't have so many, much fewer large magnitude data than NGA, then he was not sure it's applicable to large magnitude.
Yeah, well, I think that it's important to do the comparison between them is to look at the right magnitude range when we're doing comparisons. But for, they're typically below magnitude 7 is where most of their data is. But we don't, even NGA doesn't have a tremendous amount of earthquakes above 7 in it.
Linda, are you showing fees from ACAR or not? Because you had those, Nick, you had those in your Sigma comparisons, is that right? So will we see those again on tomorrow or Friday or Wednesday? Either of you, the Sigma comparisons between the models, how much ACAR's Sigma is, it's high, right? It was around 0.8 or something like that. Okay.
I am only showing CSS. Do you want me to put the fee of ACAR and others? Is that what you're asking? Okay.
I guess I'd like to get us back to a comparison of this is to his numbers, his fees were a lot higher than before. When we were just looking at the Sigmas in Workshop 2, we didn't know if it was a higher fee or a higher tau. Now we have it as a...
He's concluding that it's coming from fee.
Fee. Okay, let's just pull those up, all right? Thanks.
I think the... taus aren't particularly large, but
yeah, Linda said she has the tau values for ACAR et al. In the tau discussion tomorrow.
okay.
So that one will be covered. She didn't have fee, but she'll add those in there so we get those.
So fee, I see tau is broken out by magnitude, but fee isn't. It's only broken out by distance.
Yes, he didn't.
Yeah, maybe that big increase is at small magnitudes or something. Did he provide that, or have you looked at it?
I don't think so. I think he provided this information. So.
I think they've been a little reluctant to do a magnitude dependence because they had a, let's say, bad experience, maybe the way to put it, doing that once where you just let it go, and then it would vary tremendously from period to period. So you need to have a smooth magnitude-dependent model in there. But because of that, they went to, all of their recent models all went to constant magnitude fee, but then you're going to be getting these fees that go with your magnitude 4s to 5.
Yeah, exactly. So, I mean,
And we saw,
it's worth looking into if you haven't, just so you understand
but as we saw,
where you can believe the model.
Yeah. As we saw in NGA, we saw a significant increase in fee at magnitudes below, as we dropped down below 5.
Okay. Tom? Just, I'm still a little confused about, in the final report, what will be the longest periods that will actually be covered by this analysis? What's the longest period?
10 seconds.
10 seconds. So at 10 seconds, certainly by the time you extrapolate out the 20 seconds, it should be peak displacement, and there should be a clean extrapolation from 10-second spectral displacement to peak ground displacement. And so is there any discussion of how that extrapolation occurs and how it would compare with realistic views of slips on phones? Or frankly, I'm a little skeptical of our ability to go to 10 seconds, and maybe we should just put a line at 3 seconds and say beyond 3 seconds, especially at near source ground motions, it's tough to do this kind of analysis. I mean, but this thing will actually say 10 seconds, and we think we know the answer.
Most of the models we're using are defined out to either 5 or 10 seconds.
For some, well, the some of the Europeans go to
4 seconds. Right. So clearly, as what you agree, as you go beyond 3 seconds, we get into much harder or less empirical control on what the ground motion models are.
So I mean, so when the report comes out, would there be some clear way to say that, well, here's a model, but it's a harder problem, and we're not so certain about how to do those long periods. I mean, ultimately, we're back to what's the slip on the fault, right? I mean,
well, talk a little bit about it. So, Doug, you have something on slip on the fault that we'll get to this afternoon. So Tom, let's come back to that this afternoon when we start to go through it. I think Doug is looking at correlation of response spectral values and slip on the fault, so that may be addressing the period range. What's the longest period range you're looking at, Doug?
the analysis is done with the numerical simulations. The longest period in that case is 20 seconds, but there's a comparison against observations, and GMPE's 2 10-seconds.
Let's save that for this afternoon, and we'll get back to it.
But it's fair to say we expect to have more uncertainty.
Yes, absolutely.
At 10 seconds, then we have it 1 second.
And the models clearly start to diverge at that point as well. Less consensus. Any other questions or comments for Bob on the